Hey everyone, so in this supplemental video, we're going to explore the following two improper integrals. And these are both improper integrals because we see that infinity hanging out as the upper bound of both of these definite integrals. So in particular, what this video is going to entail is this first integral, we're going to determine whether it converges or diverges by simply computing it out exactly. This second integral, we're going to determine whether it converges or diverges using a comparison test idea. And the last bit I want to mention is both of these integrals, as we'll talk about at the end of this video, actually present a particularly fascinating idea that can happen with geometry. So without further ado, let's dig into it. So again, we're going to compute this first integral exactly. Or I should say, we're just going to go ahead and try to compute this integral the best way we can. And remember, since we see that upper bound as an infinity, this is an improper integral. The first thing we would do in trying to actually compute this thing is introduce a limit. So we'll introduce the limit as, say, our quote dummy variable c goes to infinity from the integral 1 to c. And then we have this as pi times, and we can change this using algebra to x to the minus 2. And now that we've introduced that limit, we have a definite integral from 1 to c. We can approach the integration as we normally would and ignore kind of that limit sitting out in front, but making sure to take it along for the ride. So our next step really for computing this integral is computing the antiderivative of that integrand. And well, for us, what we see is that pi is just a constant, so we could pull that out in front if we wanted to. And then the real integration piece that we need to do is this x to the minus 2. And we can compute that using the antiderivative power rule. So we get x to the minus 2 plus 1 divided by that power plus 1 as well. And of course, in this case, we don't have a plus c because this is a definite integral, but we get to evaluate that integral at those bounds 1 to c. Or that antiderivative, I should say. All right, so that limit again is coming along for the ride. What this reduces to for us is pi times x to the minus 1 all over minus 1, and we get to evaluate that at 1 and c. So if we clean this up a bit, what our limit looks like now is minus pi times, and let's plug in those integration bounds, the upper bound first. So x to the minus first is the same thing as 1 over x. So this first term becomes for us a 1 over c. And then we subtract off that bottom minus 1 over plugging in 1. And well, after we've plugged in those integration bounds, we finally get to think about what's happening with this limit now. This is the point of the problem. That integral is, we found its antiderivative, plugged in the bounds, let's compute its limit. And well, as c goes to infinity here, what looks like it happens is there's only a c in this first term, and 1 over a very, 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 very large number, this whole thing's going to go towards 0. So at the end of the day, what this integral turns into for us is negative pi, after we distribute this in, times a negative 1. So this integral turns out to be pi. All right, and since this is a finite number, we get to call this convergent. So it's a convergent improper integral. All right, so that takes care of this first integral. We saw it actually converges. Let's take a look at this second integral now. And like I mentioned previously in the video, this second integral, we're actually going to not try to compute, but we're going to use a comparison test. And the reason for this is we have a natural function that we can compare it to. As a spoiler, we're going to compare it to basically what happens to the improper integral of 1 over x. Well, more specifically, 2 pi over x, if you will. So if you remember from class, we saw that the following happened, that the integral from 1 to infinity of 1 over x dx, we saw that this diverged. And it doesn't just diverge in class, it still diverges here as well. Well, the only difference between this 1 over x integral and if we captured this 2 pi times 1 over x thing out in front, well, we could just multiply this by a 2 pi, that's a constant. It's still going to diverge. So the reason I bring this up is we're actually going to use this integral here to compare our integral that we started with to. So remember, when we're doing these types of integral comparisons, we're really talking about what is happening to their integrands. So, for example, I'm just going to write what we're trying to do is set up an inequality. So we have 2 pi times 1 over x, or just 2 pi over x. And what we're trying to do is compare to that remaining thing, that would be this square root, but still with this original function in front. So we're going to take that remaining function, the 2 pi over x times that square root thing, and we want to compare that to 2 pi over x. So rewriting that integrand that we started with, 2 pi over x, times that square root of 1 plus, well, negative 1 over x squared squared. We're trying to say which of these sides looks like it's larger than the other. So I'll just write question marks. Is this right side larger, or is this left side larger, or is this right side larger? Who's bigger than the other in this case? So this left-hand side, I'm just going to keep the same, of course, that's 2 pi over x. This right-hand side, I'm just going to do a little bit of algebra here. So this is 2 pi over x times the square root, and I'm just going to expand that thing underneath the square there. So this is negative 1 over x squared squared, or we could write this as 1 over x to the 4th. And remember, where we care about this comparison is actually between our original integration bounds, the 1 and infinity up here. So we want to set up this inequality where we're strictly thinking about x as being between 1 and infinity, because that is where our integration bounds were, again, infinity and 1. Well, the way in which we can interpret this right-hand side, for example, we see the same factor of 2 pi over x on both sides, so those things are even. But the right-hand side in particular, we are multiplying that whole square root of thing onto it. And the square root of this square root thing is a number that's going to be greater than 1, because we have a 1 plus something underneath that square root. And the other thing we're adding to that 1 plus something is something positive itself. So this whole square root is greater than 1. So if we multiply that thing that's greater than 1 onto this 2 pi over x, well, that should make this whole right-hand side larger than 2 pi over x. So what this means is, basically our inequality that we come to is that the right-hand side must be greater than the left-hand side for all x between 1 and infinity. Oops. And again, when I should have said, I was a little cavalier just now making that comparison, but all the x values we care about putting into the right-hand side and the left-hand side are all between 1 and infinity. And this inequality works out in that way. For any x we choose between 1 and infinity, that right-hand side will always be greater than that left-hand side. All right, so what does that tell us? Well, the right-hand side is always greater. So let's think about this in terms of integrals. Remember, we're going to try and integrate both of these things. So if we just went ahead and attached integral signs to both sides and took the integral between 1 and infinity, again, we will still preserve that inequality. Both of these functions on each side are always strictly positive or strictly greater than 0. So what can we say about this inequality now in terms of these improper integrals? Well, if you remember from before or in class, this integral that's sitting on the left-hand side, we saw that this thing diverged. And since that integrand is always positive, well, this thing diverges towards positive infinity. Well, what does that mean? Well, that right-hand side, we know that the right-hand side is always going to be greater than that left-hand side. They're strictly positive for all those x values between 1 and infinity. The right-hand side is larger. Well, inherently what that means is this right-hand side must also diverge, since it's greater than something that's known to diverge. So we're able to determine in this case that the right-hand side also diverges without actually having to compute its antiderivative and going through all of those other subsequent steps. So we're able to do this from comparing to something that we knew as a part of that original integral, or able to set up an inequality between something that we knew converge or diverge and what we're trying to compare to that original integral. So why is this stuff interesting? Well, if we go back to the very beginning here, we started with these two integrals. And here's an interesting aspect that I didn't bring up already. This first integral that we looked at between 1 and infinity of pi times 1 over x, quantity squared dx, what this actually represents is a volume of an object. And when I say volume, I really mean like that three-dimensional volume that we've thought about previously in geometry. The object that this represents is when we take this function, the function 1 over x. So if we draw that out, we think about that function between, say, 1, and this is going off towards infinity. So let's draw infinity on the far right-hand side. And the way we're drawing this object is actually revolving it around the x-axis. So this thing is making almost like a curvy cone shape, if you will. So maybe I'll just draw this a little bit out here. So what we computed up before for this improper integral was actually the volume of this object. And just to bring us back, what we saw was the volume of this object, or this curvy cone, was finite. Even though technically this cone kind of goes on forever, the overall three-dimensional volume that it encapsulates is actually a finite number. So that's something interesting. The second thing that's particularly interesting, though, in this problem is, again, going to the second integral now. What this second integral actually represents for us isn't volume, but it's surface area. And it's surface area of that same three-dimensional curvy cone coming from that volume calculation. So this is the surface area of this cone. And what we just saw happened was the surface area was that this integral diverged. So in terms of geometry, the surface area here is infinite. So why is this an interesting kind of little mathematical nugget? Well, what we just saw was the three-dimensional volume of this curvy cone that literally goes on forever. That three-dimensional volume is a finite number, but the surface area around that three-dimensional object turns out to be infinite. So I think this is a pretty interesting mathematical situation that we're able to use improper integrals to kind of describe. It's a very curious thing that this happens. And this is an example called Gabriel's horn. And it's one of these interesting ideas where this three-dimensional object may have a finite volume, but it has an infinite surface area.